Hi, Jeremy.
Hi, Bob.
How you doing?
Very well, thanks. How you doing?
Can't complain. Let me introduce us. I am Robert Wright. This is the Wright Show on meaningoflife.tv. You are Jeremy England. You're a physicist at MIT, where I assume you are right now.
That's right.
And there's a number of interesting things about you. One is that you have a kind of, I guess you could say, a theory of physics that is getting a lot of attention that could, in principle, explain the origin of life and might do even more than that, as we'll explain. It's also kind of a theory of chemistry, I guess. We'll get into what exactly it is. You, you're also an Orthodox Jew, and that's kind of interesting, first of all, because you weren't raised Orthodox, but chose to become Orthodox. It's also interesting because you've written a little about connections between your spiritual tradition and science. You had a piece in commentary recently that made some connections between biblical text and science. So I hope we'll have time to cover all of this at least a little. I wanted to start out with the science part. And first of all, have I said anything that's wrong so far? I mean, it is a kind of a theory that, among other things, could explain why life emerged or how life emerged.
Yeah, I try to be pretty cautious about claiming that. What I'd like to say rather is that in my research group at MIT, we like to think about the physics of how things that don't seem to behave in lifelike ways at all start to behave in ways that are particularly lifelike, in ways that are normally thought of as quite distinctively lifelike behaviors. Mm-hmm. I think talking about the origin of life, casting a glance backward at our past, is a question that's quite specific about the forensic details of what sense we can make of the past by looking at what we know in the present. And we're, as theorists in my group, much more so about the proof of principle. How do you understand the general physical question of how you go from things that seem what you might call inanimate to behaving in ways that we usually think of as being quite distinctive of life?
Okay, so you might say this theory would suggest a mechanism by which life could have arisen, but you're not an historical scientist, so to speak.
Right. Yeah, I don't have any horse in that race when it comes to the detailed question of was it on these clays or these hydrothermal vents or on these asteroids or whatever.
Okay.
I have no idea.
So let me try to characterize at some level of abstraction some of your ideas and see how close I come to the truth. First of all, it seems to me at a pretty abstract level, you're saying even in the inanimate world, with chemicals we think of as inanimate, under some specifiable circumstances, structure is likely to form. Is that fair?
Yeah, although I think it's very important to be more specific about what we mean by structured, because there are lots of things that you might say are structured, which I think don't automatically remind us of life necessarily. So I think the starting point for what we've been thinking about with some of our theoretical and computational research is trying to talk in a physical language. So talking in terms of things like energy and distance and time and mass, these basic physical quantities. What are the physical properties you can notice about living things that you would say are most distinctive of life? So what I mean by that is that I could take a rock and drop it off a tower and it would fall, or I could take a cat and drop it off a tower and it would fall. So falling in gravity is a physical property that things have, but it's not something that we think of as being distinctive of the cat, because lots of things that aren't alive do it just as well. Mm-hmm. But then there are other things that living things do, which we can still be fairly precise about in terms of physical properties. Like we could say that there is a source of available energy in the environment of the living thing, which has to be harvested by some very specific structural means, right? That you have to, as a combination of atoms, in a sense, be in the right shape in order to draw that energy out of the environment and absorb it. And when we look at many examples of living things, we find that they have those kinds of relationships to available drives in their environment. And that doesn't necessarily mean that that property is unique to living things, but it's certainly more distinctive than, say, falling off a tower. And so we're trying to be as specific as we can about those kinds of physically well-defined lifelike properties, and then think about what are the physical conditions under which those properties should be expected to spontaneously emerge, given what we know about thermodynamics.
Okay. So I think there's a common sense version of this that'll make sense to people, which is living things consume energy. And, once you get into the actual physics of it, you get more precise and you talk about, I guess, that, what they do is they consume they take in relatively highly structured energy, then they dissipate the energy, I think typically in less structured form, and that is itself actually doing the work, so to speak, of the second law of thermodynamics, which says that in the long run, that's what happens. The world as a whole becomes less structured, and that involves that process of becoming less structured involves the dissipation of energy. Living systems seem to be exceptions to that rule because they're highly structured, but really they are just local exceptions that remain local exceptions by virtue of actually hastening the more general decline of things. That is, they take in the structured energy, dissipate it in less structured form, right? And you're saying that it isn't just, for starters, it isn't just living structures that do that, right?
And so it's certainly been understood for a long time that it is not only living things that may be involved in some process of absorbing work from an external source and then dissipating heat. Mm-hmm. That is the description of a whole field of physics called non-equilibrium statistical mechanics, is studying systems that have that property. I think that when talking about structured versus non-structured and a general tendency, a hastening of disorder, I think you have to be kind of careful. The second law and entropy and these ideas are very subtle, and I almost, as time has gone on in talking about these ideas, I realized it's easier to almost just avoid talking about entropy and talk instead about work, and about heat and about probability. Because entropy, in some sense, when we make arguments using the idea of entropy or the second law, we're really making an argument about the likelihood of something happening based on a probabilistic model.
Right.
And so at the outset, when we're trying to prove the second law in a theoretical sense, we have to start by making modeling assumptions. And the modeling assumption that we make is that we have something called a heat bath, which is this vast reservoir of lots of molecules that seem to be arranged totally randomly, that are sharing a lot of energy around as they bounce off of each other. So that would be like the air around me or the water that I would be sitting in if I were in an actual bath. And in any case where we're trying to make a model, we always are making these assumptions to make the consequences of the model, when we work everything out logically, look really clean, that are idealizations. So when you have a perfect and ideal heat bath, then your statement of the second law becomes perfectly correct, that on average, over repeated observations, under identically prepared initial conditions, you will find that on average, the total entropy of the universe should seem to be increasing. First of all, even in that framework, you're allowed to have statistical fluctuations that momentarily seem to not go that way. Although that becomes less and less likely as you talk about bigger and bigger systems that are made of lots and lots of atoms and molecules.
But through randomness, in other words, a bunch of molecules could happen to come together and form a structure.
Right. So randomness is a mathematical idealization. So, I don't know that the air in the room around me right now is totally randomly arranged. In fact, to some degree, I have reason to believe it might be somewhat non-randomly arranged. But even, if I were trying to test that assumption, it would involve making more observations than I ever could make to be perfectly certain. But really what it amounts to is just saying, this is a good working model, that we find that when we make this assumption about vast reservoirs of heat that's being shared around lots of molecules or atoms, that it's a good assumption. And that's because the dynamics of these things end up being pretty chaotic, so that total randomness ends up being a pretty good model of the statistical behavior that we observe. And once we have that apparent randomness, then we're off to the races mathematically and establishing on firm footing the idea that there is this directionality to the way things should seem to behave in terms of how energy flows. Because if I put a small puff of energy into a random reservoir, it was localized and structured in some way, and it's going to get spread out and diffused around. And the likelihood of it coming back to me is much smaller than the likelihood of it spreading out.
Okay, so I gather then, let's try to talk about it without respect to entropy, but this idea that, inanimate structures can arise that kind of take energy in one form and then dissipate it. You're using the term work. That's the doing of the work in a sense.
Yeah. So work in a physical definition, what it's about is either motion or the potential for motion. Mm-hmm. And so saying you do work on something is as simple as saying you push on it over some distance, and either it's moving now because you pushed on it, or maybe you sort of compressed a spring and it can push back and make something else move. So that's the basic Newtonian mechanical idea. And then there really are two ingredients to the argument that we're putting forward and trying to test in various simulation frameworks in our group, and hopefully eventually in experimental collaborations, which is the following. First of all, when you have a system with many pieces that can be arranged in lots of different combinations, and then you also have something in the environment that's pushing on it with some pattern. So let's say there's a song at a certain pitch or light at a certain frequency. There's something changing in the way the environment is pushing on it so that it could get more and more work dumped into it over time. As I put together those building blocks in different ways, not all combinations of them are going to be equally good at absorbing work from that same source. So the classic example I think people are very familiar with in practical experience is a glass and a song at a certain pitch, right? That if I have a crystal glass, if it's in one shape, then it seems to resonate at one pitch, and I can get it to vibrate a lot by singing at that pitch. If I change the shape of the glass, but I keep the song at the same pitch, the glass vibrates less because it resonates less. And as a result, less work is actually going to get done by the song on the glass, and less heat is going to get dumped into the surroundings.
Right. And this kind of leads to why I'm a little reluctant to let go of the second law of thermodynamics. Are you saying that, that matter tends to get arranged so that work can get done efficiently?
So what we are, the general thing that we can prove is a more general statement than that. And then what it points to are particular cases where, yes, you do expect to see things that start off in a seemingly naive random arrangement essentially behaving like something that spontaneously shapes itself into the shape of a glass that's good at resonating with the pitch in its surroundings. And that's what we've been starting to explore in simulation. And the reason that we're able to say that that's happening is so getting back to this point about being in the right shape, I think one thing we have to bear in mind is that some sources of work are easy to absorb work from. Like if I hit a table with a hammer, it really doesn't matter how the table is shaped. The table's going to absorb a bunch of work and then dissipate a bunch of heat because it's not hard to absorb work from a hammer blow. But if you have like an oscillation of a particular frequency, then maybe you need a subtler matching of your shape to that frequency. If you have an even more structured pattern of some kind, then it is even more challenging to absorb work. But if you're in the right shape, then you can do that. So it's partly about how challenging the environment is. But now you get to the question of I have all these building blocks. I could put them together in all these different ways. So they're in some particular shape, which maybe is starting off as kind of random. And what's going to happen because of thermal fluctuations, the random buffeting of the surroundings at some temperature, you're going to be making little random moves in shape. And then also you're going to be experiencing this driving environment, this source of work, the song or the light or whatever is bouncing off of you and making you jiggle around. It can also be generalized to sources of chemical energy like food. And then what happens is you're going to be changing your shape somewhat at random because of the thermal fluctuations, but there's a bias to how you change your shape. And this is where the second law comes in. I don't really mean that I want to jettison the second law. On the contrary, I think our research is really about taking an extension of the second law that we've been able to prove and then looking for new and interesting consequences of it. But what I mean is that when we talk about entropy, people sometimes talk about entropy like it's this ghost in the machine that wants to make things happen. But I think that it's easier.
That's why I'm asking this, because I'm wondering if you get accused of kind of teleology, so to speak, right? I mean, it's on one interpretation of what you're saying, it sounds almost like you're saying that the second law of thermodynamics is such an important imperative in the world, in the physical world, that shapes materialize in order to let the law work more powerfully or more rapidly or something. You probably have been accused.
I definitely wouldn't put it that way. Right. And in fact, I think that it's much more complicated than that because of, well, so if I can elaborate a little bit on what I was saying before, the way to think about it is this. You're in a shape, and you're going to now make some change in shape. Sometimes you make a change in shape where some of your particles rearrange, and you're pretty likely to go back the way you came. So some shape changes are pretty reversible. They fluctuate this way, they fluctuate that way. So for example, if I were not driving the system in any way and I had a shape that had one energy and I flipped to a different shape and it had the same energy, I would expect symmetry between flipping back and forth between those two shapes because they have the same energy. But if, for example, I flip downhill in energy, I'd be less likely to flip back to uphill in energy. You're more likely to go downhill than uphill. When I start driving the system, I have to start thinking of this as being about the work that I absorb while I'm moving. When I move, I can absorb work from the drive. So I make a change in shape. And then the question is, how much work did I absorb and dissipate as heat while I did that? And the key connection here is that some shape changes that I do are going to be very irreversible, essentially because what I've done is I've used the work to go up a side of a mountain on a ski lift, and then I've skied down the other side, and now all the energy that I got from the ski lift has been dissipated as heat in my surroundings, and I'm stuck on the other side of the mountain. So I've just done this change in shape that I can't easily undo randomly. The key point here is that if you are in an environment where it is hard to absorb work, or at least where there are ways of absorbing even more if you are in a special shape, being in a special shape provides you with the opportunity to undergo more irreversible changes in shape. Because when you have more work available, you can do that ski lifting thing and drop down the other side, and then you're stuck in this new shape. So what this is about is the history of how the system evolves by changing its shape through these random local moves. And as you keep making random local moves, over time, there's this correlation that accumulates as a result of the fact that the moments at which you underwent your most irreversible changes in shape were also ones where you were specially shaped to some degree, and you were getting a little bit more kick from your surroundings.
Okay. Are there examples that are either familiar to people or that could at least be described clearly to people of this kind of thing happening in the inanimate world? So
I think a very important first example to mention is one that definitely does not have the property that it seems to be getting better at dissipating heat over time, because we're certainly not saying that in all cases everything is inexorably increasing the amount of work it's absorbing and heat that it's dissipating all the time. The same example we've been talking about with a glass. If I sing at a glass and I sing loudly enough, then what's going to happen is it's going to vibrate really strongly and it's going to shatter, right? And once it shatters, it's no longer in the shape that is really good at absorbing work from that song, right, from that pitch. So I can irreversibly change the shape of the glass so that it is much more likely to break and stay broken than to unbreak and reassemble. And the point is that in the history of the glass, in order to get into this shattered state, it had to be in this shape that was competent to absorb a lot of work from the drive, that there's this moment in its history where it was in a work-absorbing state. But you don't always see the end state looking like the state in its history. So that's a subtlety that I think in some of the popular press about what we've been doing so far has not really come through. Sometimes you end up with something that looks kind of like a shattered glass in some sense, that it bears the mark of some history of work absorption, but it has gone to some state that is not as good at it as it was in its past. But then you also have positive feedback mechanisms. Sometimes you have systems where they are doing something which is also physically consistent, where they change their shape a little bit, and they do so irreversibly, and they irreversibly get a little bit better at absorbing work. And once they've gotten a little bit better at absorbing work, then they make another irreversible change and get a little bit better even at doing that. And so you can also be ratcheting up the rate of work absorption in systems where there's some kind of positive feedback taking place. And the possibility of that kind of positive feedback is much more general than perhaps the most familiar one, which is self-replication. If you have things that self-replicate, right? If you have a bacterium and it copies itself, the first paper that I wrote about this was about pointing out, using this extension of the second law, that if you have something that grows faster than it falls apart, that is a statistically irreversible dynamics, which implies a thermodynamic background where every event of self-replication has to be generating a positive amount of heat in the surroundings.
Okay, well, when you say self-replication, are you confining yourself now to the biological world, or are there examples?
Any self-copying thing.
So what's an example of an inanimate self-replicating system?
Well, so that is going to partly depend on how picky you are on how you define a self-replicator. I mean, you could say that fire is self-replicating insofar as it is a pattern of organization, or at least a type of arrangement of the system that spreads itself, right? At least for a time, given certain initial conditions. So I think if you wanted to be more picky and say you want self-replicators to kind of be these separate and autonomous things that kind of move around, then it's really about your perspective, right? I could say cars are self-replicators, and we are their self-replication machinery in the same way that viruses are.
Right, but that's an artifact of humanity. I mean, this kind of symbiosis has been discussed between technology and the people who created us. But what about? I mean, I know this isn't a theory of the origin of life per se, but I think for purposes of thinking about it in those terms, it would be helpful to think about something that is neither biological nor man-made. A system like a.
And I think. In molecular systems, people have studied a lot of examples of this. Basically, what you need is some molecules that clump together that are also in a container that's being agitated. And then what can happen is that they can clump together and form fibrils, and then the agitation can break the fibrils, which exposes more surface area, which causes them to polymerize more building blocks from their surroundings, and then they break more fibrils. So you can have these positive feedback processes that set in non-equilibrium systems, or even in systems that will eventually reach thermal equilibrium, but they just have some out of equilibrium condition. And crystalline growth is one example.
We should quickly say, just as an asterisk that we don't have time to get into, that when you say thermal equilibrium, you don't mean what a lot of people think of when they think of equilibrium. They think of like my body is at equilibrium in the sense that it's maintaining a constant temperature. That's a totally different thing.
Oh, you're right.
Complete thermal equilibrium is like a vast expanse of no structure. So it's almost
So I don't want to say no structure. What I want to say is that it's a condition where the only thing that determines the likelihood of something happening is its energy. That lower energy things are more likely, and higher energy things are less likely, and the likelihood is determined by the temperature. And so sometimes you get structure, especially at low temperature, in equilibrium systems. And there's a whole branch of physics called equilibrium statistical mechanics that studies that.
Yeah, although that means that locally they have moved further from equilibrium, right?
No, so you can.
Well, actually, I shouldn't move us further along, except to say that a human body or biological system is actually, in thermal terms, far from equilibrium.
Absolutely.
Because there's so much order and structure, and it's blah blah blah.
Yeah.
So okay, so broadly speaking, what you're talking about reminds me of what are sometimes called self-organizing systems. You're familiar with all the history of talking about this. I'm sure the kind of Santa Fe Institute crowd and people like Ilya Prigogine and people like Stuart Kauffman and so on, and they sometimes bring up examples of self-organizing systems like tornadoes or vortexes or whatever, and I guess those things can be self-sustaining for a time. But is this, I don't know, what, and maybe in a loose sense, self-replicating, are these, do they fall under your rubric as well, these kinds of things? Or are there other examples you would point us to, if not?
So I think that, the history of the literature of self-organization is certainly very interesting. And I think people have, you mentioned Ilya Prigogine, been intrigued for a long time by the question of how you start thinking about thermodynamics in a way that helps you make sense of the kinds of patterns and organizations that you see emerging under different kinds of non-equilibrium conditions where you have some source of energy that's available. I certainly have nothing specific to say about tornadoes right now. I don't understand them any better than someone with a college education in physics, because I haven't studied them. But I think that you can say that whenever you have a system of this kind, that when you have a structure that emerges on a short time scale and sticks around for a long time, that is a statistical irreversibility, meaning there's a sense of forwardness rather than that there's a forward relative to backward that's more likely. That is the signature of a process of absorbing work from a source and dumping that energy into a surrounding bath. That doesn't always mean that it is easy to explain why the structures are shaped the way they are. And how easy that is, I think, will depend a lot on the specific system. And I think actually some of these systems that people studied at the beginning of studying pattern formation and self-organizations are actually quite difficult because they're often fluid dynamical and they're harvesting their source of energy that they can do dissipation with from things like two different baths that are at different temperatures or two different surfaces that are moving at different velocities and things like that. I'm finding in what we study in simulation, where we have a lot more control, it's a lot easier if you pick something like a driving frequency and you are applying that force to a particular particle in the system and you can watch how the other particles in the system attach to it, that I think there's a lot of opportunity to understand these phenomena better in cleaner systems that are designed not for the wow factor of how pretty the pattern looks necessarily at the end, but rather the exquisite control you have over the physical properties of the system so that you can track things like work going in and heat going out and connect that to structure in a way that allows you to say, oh, this structure is different than that one, and here's how.
Okay. Let me switch frames slightly. I mean, as I said, one way your work is kind of tantalizingly described when covered in the popular press is it may have applications, could explain the origin of life or something, even if that's not really, strictly speaking, what you're up to. Another thing, and I think this is a quote from you. You said you might call Darwinian evolution a special case of a more general phenomenon, which is to say the phenomenon you're studying. By that, I take it you mean that, well, you could look at Darwinian evolution and say, well, it creates structures that are good at absorbing work, absorbing energy in one form, dissipating energy in another form, that they're very good at kind of harvesting the available work. And what you're saying is that's true. There are those structures, but then again, there are those structures in the inanimate world as well. So it's in that sense that Darwinian evolution may just be a special case of a more general phenomenon, right?
Yeah, I think what we feel that we have a theoretical argument for now, which we're trying to test out, is why you should see spontaneous emergence of structures that look like they are very fine-tuned to their environment in terms of physical properties like work absorption. And I think when you have self-replicators, and you can make this whole Darwinian argument, that works because being good at absorbing and dissipating energy becomes synonymous with being good at growing fast and not falling apart fast. But when you don't have self-replicators, you can make a generalization of this argument and still say there's a broader class of conditions under which I should have something at the end that looks like it is, in a sense, good at solving a hard problem. So it looks like it's adapted to its environment in such a way that it will seem like it has, you were talking about teleology before, it will appear to have an apparent function insofar as I've presented it with this environmental challenge in terms of how to absorb work, and it has met that challenge by becoming shaped a certain way. And I can understand that by thinking about its antecedent shapes, its history, in the same way that with the Darwinian argument, I can understand the adaptation by thinking about an organism's ancestors. But in the case of this more general argument, I don't need to start off by saying, oh, here are finches or here are bacteria and they make copies of themselves. I can just say, I have a bunch of particles, they're randomly arranged. What is the bias in how they're going to start locally rearranging themselves?
Mm-hmm. I would imagine some evolutionary biologists would give you a little pushback on that phrasing. I mean, they may just get a little defensive when you say that the Darwinian theory is just actually a special case of a more general and deeper law or something. And I think they would say something like the following. And interestingly, I'm not sure that the following is any different from what you just said. But I think they would say, well, first of all, I mean, there's something different about the reason that biological structures are good at absorbing work, which you alluded to, which is that because of replication and variation, there is relentless competition to choose those forms that are best at absorbing work. And you go along with that. I mean, I guess maybe what you're saying is just that, okay, there's a tendency under certain circumstances, even in the inanimate world, for structures like this to form. Then at some point, for reasons we're not totally clear on, you get structures that not only form but replicate themselves. At that point, you've got natural selection, and you have a whole competition that systematically selects for forms that are good at absorbing work in increasingly kind of complicated ways.
Yeah, so I mean, certainly nothing we're saying seeks to in any way replace or supersede what people already understand in the language of biology about the whole grand pageant of Darwinian evolution. I think it's more that when viewed from a physical perspective and talking about the thermodynamics of what's happening, there is a sense in which such a process can look to be one example of a more general physical phenomenon. That doesn't mean we don't need to talk about biology anymore. I did my undergraduate degree in biochemistry. I love biology, and I don't want to say that physics is a totalizing language that supersedes the biological one. I want to keep those languages separate, and I want to translate between them, and I think we can benefit greatly by facilitating that. But I think that when looking at things in physical terms, I think what's interesting is that it's about how this alters your notion of how special or adapted or apparently functionally organized something can seem to look without having this Darwinian explanation for how it got the way that it is. I think that if I were to say something at all, I don't know, critical or at least provocative with respect to how I think sometimes biologists look at biological systems, I think people often incline towards the attitude or the instinct or the reflex that when they see something in a biological system that looks like it is useful and good at something, that must be the result of rounds of selection at the level of self-replicators competing and trying to copy themselves and survive and all of that. And I think that in a majority of cases, that must be part of the story. But we also have to ask ourselves, before there's a self-replicator, like anything we would point at and say, here's a self and it copies itself, what is the toolbox that we have of stuff that's just lying around far from equilibrium that's actually kind of useful and structured and organized in ways that seem subtle in some sense with respect to the environment? And we should perhaps expand our notion of how big that toolbox is once we think carefully about the physics, that it's not like before Darwinian selection, before the chicken and the egg, you just have garbage lying around. You may have things lying around that are much more useful than that.
Right. I mean, I guess one thing evolutionary biologists might say in reply is, well, of course, there's a toolbox, so to speak, in the sense that there are laws of physics, and any forms that win the Darwinian competition are going to have to do a good job of harnessing the laws of physics. I mean, the laws of physics are part of the environment, and we all know that organisms get adapted to environments through natural selection. So naturally, they would harness the second law of thermodynamics and so on.
I mean, it all has to be consistent according to the assumption that it all works by the same physical laws. But I think, once you're making that argument, it's almost like saying there is nothing to explain about the origins of life. But it happens, so it must be according to physical laws. And so why should this bother us? And I think to the extent that people wonder about that, or it sort of captures their imagination, I think it's because right now the intuition maybe is a little bit limited in terms of what we can imagine as the beginning of the process. Like, it's hard to understand how this gets going because we think of something that appears to be at all functional or at all specialized or at all adapted to be difficult to realize without the Darwinian mechanism. But I think that if we're doing anything that pertains to that whole question, and I really, I to some degree, I try to be cautious about saying anything like that because, as I said, it's really more about a proof of principle in the present. But if we're saying anything that has to do with that, it's about perhaps altering our sense of likelihood or ease of getting structures like this by accident.
Mm-hmm. Yeah, I guess the last thing I'd say about a kind of reply you might get from evolutionary biology is, in response to this idea that maybe Darwinian evolution is just a special case of more general phenomenon, I think they might say, well, wait a second, no, there's a real threshold cross with the origin of life in the sense that, to some of them, a certain kind of teleological language does become appropriate. So even like Dan Dennett, emphatically Darwinian philosopher, will say it is fair to talk about organisms as having goals and purposes imbued by natural selection, and to say, for example, when I eat, the purpose of my eating the food, and that's a form of absorbing work, doing what we're talking about, right? The purpose of that whole eating behavior and the whole eating apparatus, the purpose of this particular form of absorbing work is to sustain the structure that is me. He would say it's fair to talk about purpose at that point, purpose imbued by natural selection, not a god in his view. Whereas he would say before you've got natural selection, he would not want, even if you can show him these forms that do arise, perhaps even predictably under certain circumstances, that are good at absorbing work, he would say you still can't talk about it being their purpose to absorb the work until you have natural selection through replication and variation.
In a sense, I totally agree with that. And I think we're sort of splitting the difference in what we're doing with our active areas of research in the group, because we have one grant from the Templeton Foundation, which is all about going after this question of, okay, how do you get self-replicators? What is the next step? So you have these non-equilibrium self-organized structures. When does that translate into the emergence of things that look like self-replicating things? Because we obviously think self-replicators are important and interesting, and that obviously is another piece of this question of how you get life. Although also we have a different grant from the Moore Foundation to study what we're calling emergent computation, where just to complicate this question about teleology and remind us that it's largely a matter of how we want to define things. The question is, how smart can you get something that's not alive to act, right? If I have a collection of particles and I start poking it in a way that's patterned, can I make a physical argument for conditions under which this thing is going to spontaneously become organized in ways that essentially look like it's behaving, let's say, predictively? So that there's a physical equivalent of it's taking out an umbrella when it gets cloudy, but before it rains, because of all of the history of experience that it has already been able to interact with. So I think that if you have something that in complex ways behaves predictively, I don't think you necessarily want to call it alive, but it's certainly going to reset your notion of what the types of behaviors are that are unique to life.
Mm-hmm. And yeah, and again, a biologist would say organisms behave predictably because they've been selected to, by virtue of, as you said, the history, not just their own personal history so much, the history of the lineage.
Yeah.
So okay, so let's with all that as background, let's try to take advantage of the remaining time to talk a little about the kind of spiritual and religious issues. I mean, first of all, you are if you're Orthodox, I take it that means you're religious in a theistic sense.
Well, I think Judaism is
right. It's more complicated than with Christianity. I know.
Peculiar religion when arrayed next to many other faiths, and I think it's in many ways all religions are so different from each other that it's kind of hard to make a common language for classifying things in each of them. What I would say is that I can't speak for all or even most or even a plurality of Jews, so I'll talk about what makes sense to me. My understanding of Judaism and of the Torah is that the principal concern should be with what one says and what one does. And
so with ethical guidance?
Not only ethical, so ritually also, because much of Judaism is ritual that involves both action and speech. At a certain time of year, you take a certain bundle of a certain kind of plants and say a blessing and shake them in the air. And I see a real purpose in that. And that does not necessarily automatically make clear what it is that I believe. I think belief is a very complicated thing. And actually, the Hebrew Bible is one long discourse on what belief is and what actually substantiates belief. So I think what's very tricky about this is I think sometimes when people start off they're talking about it as though we start off knowing what God is, and then there's this question of do we believe in God or not? Whereas I would say rather that words get their meaning from the context of their usage, and that I see the mission of a Jew trying to keep the Torah as trying to clarify the meaning of all these names of God that there are in the Hebrew Bible by providing the right context for the usage of those names in action and in other words.
Okay, maybe a related question, rather than let you off the hook entirely. I'll ask maybe to some extent the same question this way. You said ritual has a purpose. Do you mean that you can see that it's good for people to have rituals, which, rites of passage and so on? Or do you mean a purpose that is in some sense imparted from somewhere other than the human sphere?
So I think that the Torah's examination of this question is quite elaborate, and it's very hard to summarize. But I think that, to say something, the thing that comes to mind that allows me to express the point as briefly as possible is that in his commentary on the mitzvot, on the commandments of the Torah, Maimonides, the famous sage, from the, I think, 13th century. I always forget whether it's the 1200s or the 12th century. I think the 13th century. In medieval Spain, relays from the Talmud that the sages of the Talmud said that there are 613 mitzvot, there are 613 commandments, and those divide into 248 parts of the body and 365 days of the year. And, 365 days of the year is kind of easy. That one, we know 248 parts of the body kind of sounds like, okay, well, you just took 613 and subtracted 365 from it. That's where you got that number. Because how many parts does the body have? Obviously, you can slice it into lots of different pieces if you want to. But I think that homiletically, what that point makes very well is that if you try to dissect this whole, if you take each thing separately and you examine it, you take a heart and you put it on a plate, you take a lung and you put it on a plate, it becomes more difficult to tell what it's for. And that relates to some things we were just talking about.
Mm-hmm.
Obviously, you can still tell a heart is better for doing some things than others when it's on a plate. But what actually makes it work is the context of the whole in which it operates. And that doesn't mean the different parts are all equally essential in some sense. Like I could, clip a hair off my head and I'd still be me, much more so than if I took out my eyes and my brain and my heart. And yet there's this whole that cooperates and each part plays a role. So I think when you talk about rituals in the context of the Torah, it's very hard when you talk about an individual one to say, here is its full freestanding self-justification. But when you live your life this way, it fits into the context of all the other ones, and you see the connections between them, and different things remind you of different other things. So I also have to add, I'm not at all a mystic, and I don't like positing sort of invisible and unsubstantiatable other dimensions to the world, which can't be assayed empirically and experientially. And so when I do things to keep the Torah that involve reciting a blessing and shaking some plants in the air, it's not that I'm now imagining something magical happening. In fact, the Torah, is very anti-magical when it comes to certain verses that you could point to. But that doesn't mean I don't think it has a purpose, because it provokes analysis. Why am I doing this? What are the different pieces of this? What constitutes doing it correctly? What constitutes doing it incorrectly? What do those pieces mean as signs? How can I analyze them? And then that's been the work of Torah study for thousands of years in the Jewish tradition. It's all a giant, elaborate, unending conversation piece that expands and develops your knowledge of God.
Okay, so what you said about not being a mystic, does that mean that you believe that if there is, or assuming there is, a God in some sense of that term, whose will is being manifest in the world, that manifestation would be through the laws of physics?
So I certainly see support for that notion in some verses in the tradition. For example, in Psalms, there's a verse, I'm going to forget the number, but I know in Hebrew it's Ma rabu ma'asecha Adonai kulam v'chokhmah asita, which means how manifold are your works, O Lord, you made them all in wisdom. So this word chokhmah, wisdom, if you actually look at how it's used in the Torah and you try to say, all right, what does this word mean? What is it used to refer to? What does it mean that he made them in wisdom? The two cases in the Torah itself, the first 5 books of the Hebrew Bible, what's sometimes called the Pentateuch. I don't know if I pronounced that right, but in any case, that is, there are 2 places where it's referred to multiple times, at least. And one is in the building of the temple. There are all these crafts that different members of the tribes of Israel have to perform. They have to pour molten metal, and they have to weave things, and they have to dye wool and all of that. And that each person who has that skill, they're referred to as having chokhmat lev, like the wisdom of their heart to do it. So that wisdom in some sense is about a praxis. It's a craft, the ability to interact with the world and understand that which is reliable and reproducible about its behavior, and to turn it to your will by treating it a certain way. And I think that really refers to the law-like behavior of things. You can't do an experiment without craft in some sense. The whole point is control and reproducibility. And the other place that I think of that it's referred to, this idea of wisdom, is Joseph, the son of Jacob, who is in Egypt, and he's prognosticating about the future of the agricultural cycle of the Egyptian economy, and giving Pharaoh good advice about how to store grain before there's a famine and all of that. That there's a sense of the predictability of the world, again, that's being invoked when he's being referred to as being so wise. So, I think that definitely the Jewish tradition and the Hebrew Bible very well encompass the notion that the world is pretty predictable in many aspects, and even in some aspects that don't initially seem predictable, but if you really are clever, then you can work them out. And when we predict the world, we do so by making models of it. And those models are reliable to a certain extent. But when we talk about the laws of physics, I'm just a little bit reluctant to simply say yes to what you said, because I want to emphasize that the laws of physics are things that people made up, right? These are models we have made of our observations and experience, which help us consolidate and summarize that which we understand, which is predictable. But I don't so much like the idea that the laws of physics, as we have developed them or envisioned them or know them, are like something that has already been preset or written down by God, because then that just provokes the question, well, what happens when something seemingly impossible happens? Does that mean we didn't know the laws of physics? Or does that mean that the laws of physics were violated by God or something else? And I think that points to the philosophical confusion that arises when we treat laws of physics like things that are written somewhere other than where people have put them.
Right. And in your piece and commentary, which I mentioned, and which we'll provide a link to, you use the term partly predictable. And I think you're kind of celebrating it, because I gather in your view that leaves room for free will.
Yeah, so I think that it's I would say it's the sort of balance point where notions of agency and individual responsibility become possible. Because if you look at a world, you try to imagine a world where nothing is predictable at all, then obviously there can't be anything in that world or any responsibility in that world. So, all these kind of philosophical parlor tricks for an undergraduate ethics class. If everything is random, then we have no moral responsibility. If everything is deterministic, we also have no responsibility, because someone else set the initial conditions and we're just slaves to it. And I think that the point is the perspective of the human being is somewhere in between. The world is somewhat predictable and somewhat unpredictable. And we don't each ever have certainty about what the other is going to do, or what the world is going to do for that matter. And I think that uncertainty leaves open our perspective to contain the idea of choice, the idea of different possibilities that are unknown until they are realized. And I think that's part of the message of this verse that comes to Moses when he's at the burning bush, and God says to him, you should tell the people, you should identify me as Ehyeh Asher Ehyeh, which means, or is often translated as, I am that I am, or I will be that which I will be. It really is kind of a future tense. So it's kind of, I will be that which I will be. What happens isn't anything until it happens. And that's a logical and epistemological constraint that we can't get around no matter how clever we get.
Well, you can imagine a completely determined world in which the future is implicit in the present, but physics itself isn't completely determinative these days, deterministic these days, right? But the main loophole, as I understand it in modern physics, the main loophole you hear about is quantum indeterminacy, which is typically cast as just randomness, a kind of coin flip under certain circumstances at the subatomic level. And a lot of people don't find that to be a satisfactory source of something you could call free will, right? I'm just wondering, you're a physicist. Do you think about these questions? Like, okay, where in current physical paradigms would there be room for free will? Quantum indeterminacy is one, or what?
Well, I guess I'm not as bothered by this question as I used to be, actually. When I started learning physics in college, or I guess beforehand, but also in college, and I was also reading these kinds of philosophical questions, it interested me a lot and sort of worried me. And I think it doesn't bother me as much now, because I take my own will much more so for granted as the starting point, or the thing that I'm more sure of as the foundation of the reality that I experience. And then these other things like electrons or quantum theory or statistical mechanics or what have you are really great. They're really fascinating. They're really useful. They're very applicable to that which is predictable about the world. but they are models that we have developed of the world, and their appropriateness for explaining observations that we make and helping us make accurate predictions does not make them the world itself. So, quantum mechanics contains randomness, but I don't actually see as much of a distinction there as I think some do, because practically speaking, there is no experiment you could do where even your knowledge of classical physics would allow you to say, I expect no randomness whatsoever to enter into the result of my measurement. And the fact that the randomness in quantum mechanics looks more fundamental on paper is really just an accident to the fact that the models we make in classical physics seem like they are deterministic on paper. The question you have to ask yourself is, why do we think in classical physics that a cannonball should have a height off the ground, which is a number that is true about it, if no one measures it, right? We should just be talking about...
You mean that we just can't measure it with infinite precision as a practical matter?
No, not even that, but just that if I tell you I fired a cannonball in the air yesterday, and I'm not going to tell you anything more about it, and no one else was there, and no one was looking at it, and no one held a ruler up to it or anything, why would we say there is a number which is true about the world, which is the height that the cannonball had off the ground, but no one measured it? That actually, I think, is, that's a longer discussion, but epistemologically, I think even in the context of classical physics, that's a strange thing to assert. Like, you're actually painting a sort of unnecessary mystical backstory into classical physics that doesn't need to be there for you to make accurate predictions and test them. So then when we do quantum theory, suddenly it's like, oh, well, you need to stop thinking about these quantities having definite values when you're not measuring them. And so I think quantum theory was kind of reminding us, in a sense, of a philosophical mistake people had been making in their understanding of classical physics.
Yeah, although at the quantum level, there were experimental results which made it basically impossible to think of them as having these fixed measurements prior, or fixed quantities prior to the measurement.
Absolutely. So, quantum physics absolutely has scenarios that you can construct under very controlled conditions where your theory tells you that there are fundamental limits to precision and accuracy in the measurement of one thing when you have already constrained the precision and accuracy in your measurement of something else. And that's a really earth-shaking realization that I think profoundly affected people's thinking and was an important development in the history of modern physics. But I guess what I'm saying is that the idea that there is fundamental randomness that comes from quantum mechanical behavior, that still is a paradigm for modeling the world. And we don't actually, the same way we don't get perfectly straight lines, and the same way that we don't get perfect circles when we draw with a sketch pad, but that these are idealizations that help us make sense of what we can draw with a sketch pad. Mm-hmm. Similarly, we don't ever get pure quantum states. We don't ever get perfect operators that only act in the way that the simple, sophomore quantum mechanics class operators are supposed to act. We always actually have a messy experimental apparatus where we're turning knobs and trying to make the world act as much like our idealization of it as we can. And that's where these ghostly quantum effects are the clearest. So I think that having an attitude that is fundamentally rooted in the perspective of the individual who is now asking, what is the basis for believing things about the world that is going to come from my experience, and not losing sight of that. To me, I think that's important in not getting tripped up in some of the philosophical confusions that can emanate from starting with the idea that I am quantum uncertainty, and then my experience is an illusion or something like that.
Okay, now we're almost at an hour, and I know you've got to go before long in any event. So, final question. Now, I know you're saying that your work is not about the origin of life per se. On the other hand, it has implications. It suggests a kind of mechanism that could have made the origin of life more likely. Mm-hmm. And there are certainly people who would say that to the extent that the origin of life is a likelihood by virtue of the laws of physics, by virtue of the structure of reality, that adds weight to the case for a larger teleology. That, you know, the idea that the universe is designed in some sense to give rise to life, or so on, and so on. And I assume the fact that this is a kind of interpretation of this kind of work has not escaped your attention. And it may be something that people bring up by virtue of the fact that, unlike many sciences, unlike many physicists, you are avowedly religious. What do you have a take on this? On whether that logic makes sense to you, for example, that inference makes sense?
So I've discussed this and a lot of other related things with people who are both religious and not. And I think that what I find is the same observation about the world often can seem to mean that there must be a God who made the world, or the complete opposite, depending on who's looking at it and how they're disposed to react to it. So some sort of hype and buzz that ran ahead of us about the work that we've been doing has led people who are avowed atheists to contact me very enthusiastically, you know, because they're really happy that this sounds like a stake in the heart of intelligent design and creationism, because now you don't need life to beget life. You can beget life from non-life. I, by the way, am not a subscriber to any kind of view that you might call intelligent design or creationism. But what I would say rather is that our understanding of what the Hebrew Bible means when it's talking about creation should be considered a challenging subject that we can't just dash off, and we have to delve deeply into that before we even begin to ask the question of what it makes sense to say about the truth of a biblical account of creation or not. But leaving that aside, I think that every time one person, you know, will point to something and say, "Oh, well, this shows that there is design or purpose, and life has been written into the fabric of the universe," someone else could come around and say, "Well, you don't need a creator, I guess." And I think what in either case this is really about, and I think this is why, and according to my understanding, why the Torah submits itself as a covenant, as like a choice to be a party to an agreement in a sense, is because there always is this individual choice and attitude about how to react to experience. No amount of pondering, I think, can fully address for us the question of why the world is the way it is and not some other way. And then now the question for any one of us is to ask, in the face of that existential dissatisfaction or lack of complete knowledge, what will be my attitude? And I think you could take either one, and which one you take is a choice.
Okay. Well, thank you for so patiently answering such a broad range of questions. It's fascinating work. As I said, we'll link to your commentary piece, but also to at least one of your scientific papers, and people can Google your name, and a lot has been written about what you're doing, and with good reason. So thanks so much for taking the time, Jeremy.
Thank you. It's been a lot of fun.
Okay. Take care.